All right, let's approximate some functions with polynomials here. Now I have this cut out from the book because I'm gonna scoot this up here, because this little paragraph in the book I think is awesome. So here the moral of the story that we're going to be doing right now with approximating these functions is we are going to use something that's super easy to work with, a polynomial, in order to approximate some algebraic function. So yeah, I'm just going to read through this a little bit. An important observation motivates our work. To evaluate a polynomial such as this, all we need is arithmetic. You're just adding, subtracting, multiplying, and dividing, like basic stuff. Super easy derivatives, right? All these super easy, basic things that we're looking for. However, with algebraic functions, something freaky deaky like this, and trig functions, these are a lot of times called logarithmic exponential. A lot of times these are called transcendental functions. All right, the transcendental functions here, these algebraic, logarithmic, trigonometric stuff, cannot easily be used with arithmetic. Therefore, it makes practical sense to use the simplest of functions, polynomial, to approximate more complicated functions. So what we are actually going to do is we're going to say, okay, and this is not, I'm not approximating the entire function, but a lot of times you just want to look at a little piece. So if I'm just concerned with point A to point B, just this tiny little piece of data, then I can come up with this polynomial that's going to help with that piece. And then polynomials are a whole lot easier to work with. All right? Okay, so the polynomial we're going to be using is called Taylor polynomials, or what we're going to be going for here. So let's write out this definition. It's a rather lengthy definition, but it has lots of good info in it, so we're writing it out. The definition of Taylor polynomials. All right, let f here be a function with f prime, f double prime, so first derivative, second derivative, right? All the way up to the nth derivative here, defined at a. So that's the kicker. I'm defining it at a specific value, and that's the key. So we're taking it and we're just centering it around a specific value. I'm not talking about the whole thing. I'm just centering it around this specific value. Okay. The nth order Taylor polynomial for f with its center at a, f my function, with its center at a, denoted p sub n, has the property that it matches f in value, slope, and all derivatives. Up to the nth derivative at a. That is, oopsie daisy, I'm gonna scoot this up a little bit. That p sub n of a equals f of a, p prime of n, p sub n prime of a, because a is my input. So my first derivative is equal to f prime of a, so on and so forth. The nth derivative of this function is equal to the nth derivative. The nth derivative of my polynomial is equal to the nth derivative of my function. All right. The nth order Taylor polynomial centered at A is this formula. I'm scooted up again. This is a long one, I told you. The nth order Taylor polynomial centered at A is this. P sub n of x equals f of a plus f prime of a times x minus a plus the second derivative of a divided by 2 factorial x minus a squared plus more of that up to the nth derivative of a over n factorial x minus a to the n. More compactly, scooting it up again, my nth degree polynomial is equal to the sum from 0 to n, so that specific amount of c sub k x minus a to the k where the coefficients are, wait, I'm going to change this. So I'm just writing this down. So this is what we're actually going to do. This is my generic here. So this c sub k, then I'm going to be more descriptive here with this c sub k. So where c sub k actually equals f to the k of a over k factorial, for k is equal to 0, 1, 2, all the way up to n. All right. So typically how you write this, I'm going to scoot this over here just a tad. We're going to use this here. This is going to come to light here a little bit more. So this is really looking like my polynomial here going from 0 to n of my c sub k here is the kth derivative of f centered at a all over k factorial times x minus a to the k. So it's mimicking my term here. Do you see that? So this is saying generically whatever this coefficient is, and typically this coefficient is that's why it's c sub k, is what we're actually getting here. Okay, so now let's talk about this here for just a second, and then we're going to do some examples, but I want to talk about it a little bit first. All right, Taylor polynomials. Here's some key things. The big deal whenever it comes to this Taylor polynomial is that it has a center here of a. So it is centered around a value. All right, that's important. So I'm not saying that this is a complete total representation because the actual function has its own thing. I'm just saying centered around a, we're just taking a piece of it. A piece of this transcendental whatever type function that we talked about up here. Any of these kind of things, logarithmic, exponential, trig, algebraic, whatever, they don't look as nice, right? And they're not as easy to work with. No problem. If I just want a piece of it here centered around this a, then I can just see that the behavior is going to be the same. It's super easy to take derivatives of polynomials, right? Super easy. So if I'm just concerned about a little piece, I can really work with my data if I make it into this polynomial. All right, then you can easily work with your data and you can say, oh, from here to here, this is what we're doing and what we're working with. Then we can look at it in terms of this series, because a series is just a sum of terms, right? So this polynomial is sum up these terms, and this is the pattern. We're going to deal with this more in a couple of sections when we talk about Taylor series. So this is going to be our setup for Taylor series. However, right now we're just focusing on our polynomial. This polynomial is the key that we're focusing on right now. All right? Okay, so what I would do if we're looking here is this is something we're going to use a whole lot, so I don't really want to say memorize it because we're going to use it a whole bunch. But this is my spiel in terms of these polynomials and what I would say. So I went to a conference one time and I sat in on a session where there was this engineer from Boeing. All right. And his job was and he was a retired engineer. So he just came back for different special projects because he was super good at his job. But one of the projects he had was, okay, on these planes, when is it the breaking point? So where is the breaking point for these planes on the wings? How much pressure can they take before they break? What do we have to do to engineer this and make these as safe as possible, right? That's the deal. And that was the experiments that he was conducting. So he's going through here, and of course there's all this crazy stuff, and he just kept saying, okay, break this down into something we can work with. How close is this to the data around this specific breaking point, right? How close is my data going to be? Can I get a smaller degree polynomial because I can work with that better? What is my degree of closeness here? How close can I get this in terms of a polynomial so we can work with it? All right. Taylor polynomials, Taylor series are super common in engineering. So that's my plug for this. Making it into something that's easy to work with. These Taylor, this is application type stuff is what I want to say. So yes, we've been doing a bunch of series and we did a bunch of tests that last chapter on a bunch of different kinds of series. We'll be using some of those tests, but this now is more of an application. We're not going to be able to do a whole lot of application with it. I'm just putting tools in your toolbox, but this is something that can set up for application, okay? All right.